Other places where you see the Doppler effect. I don't know if this ever happened to you or somebody you know. Police officers can monitor the speed of cars using a radar gun, or in athletics, you can use this to clock like pitching speed. And what you're doing is you're sending an electromagnetic wave out. So the police officer sits there in his car, he sends the wave out. And if it hits an object that is moving toward the police officer, then as it bounces off, the object acts as the source of waves as the waves bounce off of it, and the waves get compressed and they come back at a higher frequency. And the radar gun can measure that shift in frequency and calculate the speed of the car relative to the police officer. And it can hold up in a court of law whether that person is speeding or not. Doppler radar. Have you ever seen one of these kind of like circular looking radar installations? There are some on some of the buildings in downtown State College or AccuWeather out on Science Park Road. These are Doppler radars, and they send electromagnetic waves out, and Doppler radar picks up objects in the atmosphere, so like rain, ice, snow, things that are in the air. And as things move toward the Doppler radar, it shifts it to shorter waves, and as it moves away, shifts it to, so it measures relative motion of things in the atmosphere. The Doppler effect is also prime evidence for the expansion of the universe. Where does the idea of a Big Bang come from? The idea of the universe expanding, how do we measure that expansion? How do we know that it was much smaller in the past? When we look at objects in the sky, we know exactly what kind of light hydrogen should give off, and stars are all made out of hydrogen gas. And just about every star in the universe is redshifted, meaning that they're all moving away from us and moving away from each other as well. And we can look at different places in space and measure how fast things are moving based on how shifted the light is. Another interesting place, and this doesn't have to do with light, this is just like water waves. If the Doppler shift becomes very extreme, in other words, if you go so fast that you're actually going faster than the waves you make, then no waves can get in front of you. And waves in water travel pretty slowly. They only travel about 5 to 7 miles per hour. So it's pretty easy for a speedboat to go faster than a wave in water. And when you look at a boat from above, you can see it's created this wake behind the boat, and that there aren't any waves or ripples in front of the boat because the boat's going faster than the waves. They can't get ahead of it. What ends up happening, the reason why you get a wake is the same thing that happens when a fighter jet goes supersonic and flies faster than sound. If it's going faster, notice that, again, we get these circular ripples for the sound that the jet makes, but then the jet, rather than being inside the circles, it actually gets ahead of the circles. And the circles all end up behind the jet, and there's no sound in front of the jet, which is, if this guy's standing here on the ground, he hears absolutely nothing. He watches the jet fly over his head, and he still can't hear it until this cone, this called a shock wave, hits his ears below after the jet's past him. And it's interesting, you can see constructive interference is going to happen, because look where all these crests of these circles line up along this dotted line. Okay, so we end up with a very high amplitude wave right here, a really loud sound. And that's what a sonic boom or a shock wave is. And in this still photo, you can actually see the water droplets condensing around the back of the jet, around its cone, its shock wave that's creating a really high pressure. Anything that travels faster than sound will do that, whether it's the tip of a whip or a bullet or a fighter jet. And then this one's kind of fun too. It's called Cherenkov radiation. If a particle that's giving off light travels faster than light, now that sounds like it's wrong. Nothing can go faster than light, but that's only true in a vacuum. The speed of light in a vacuum is the speed limit. But when this is a picture of a nuclear reactor, there's one on Penn State's campus, not too far from here, that's underwater. Water is a great way to contain a nuclear reactor and shield from particles. But when those particles go flying off the nuclear reactor underwater, light travels slower in water than it does in air, right? The index of refraction slows it down. So the particles can actually go faster than light in water. And when they do, it creates a shock wave of light, kind of like a sonic boom that creates this ultraviolet blue high energy light as it gives off. So this blue glow you get from a nuclear reactor underwater is basically a light shock wave. Yeah, it's extremely blue shifted. It's a lot of the light's in the ultraviolet spectrum, and some of it's in the visible blue. This is from the comic The Watchmen. One of the characters, superheroes in that is Dr. Manhattan is radioactive, and so he gives off Cherenkov radiation, which is, I think, attributed to that. So here's what the data sheet looks like. Again, SL, you get the equation for the Doppler shift of light, Okay, so we got the speed of the object relative to light, something giving off light, and then the shift wavelength. And then for higher level, you get the sound. Okay, sound or other waves, moving source. And they even helpfully put moving source and moving observer. I forgot they put that on there. So if you're in SL, you only have to check out this first example, and then you could go ahead and start the activity. You have a kind of a shorter activity to do. And then HL, I'll do a couple examples with the other equations too. So let's see. Here's what a sample problem might look like. So this has SL, but it's HL as well. So SL or HL, responsible for a problem like this. A strong emitted wavelength of such and such nanometers, kind of a red color, comes from a common electron transition. Boy, who wrote this? Strong emitted wavelength comes from a common electron transition. This should be in, not the word is. In hydrogen at rest. Okay, so this is, if you got a tube of hydrogen in your classroom and you looked at it through the spectroscope, this is one of the lines you'd see on that spectroscope through diffraction grating. Okay. When we look at a distant galaxy, we notice that instead we're getting that same line is showing up at a different wavelength. Okay, what does that tell us about the galaxy? It's the same line in the pattern, but it's a slightly different shifted color. Okay. So this one's given not in terms of frequency, but in terms of wavelengths. So I'm going to use the wavelength relationship here. The shift in wavelength compared to the wavelength is approximately equal to the speed over the speed of light. Okay. And I can use the numbers here. The delta lambda is how much shift has occurred. So it's the difference between, so that when it's at rest, it should be the 656, but it's coming up at 752 instead. So in the numerator, I'll do 722 nanometers minus 656 nanometers. So that's the amount of shift, the delta lambda that's occurred. And then when it's at rest, I'm going to need to make sure to use the right lambda for the denominator. It's what the actual wavelength is with no motion, is 656.28 nanometers. And I know nano is 10 to the negative ninth, but I don't really need to put that in. I just have nanometers over nanometers. It's just a ratio of lengths, so I could put it at 10 to the negative ninth or just leave it as nanometers. Might as well do that. And then what we could do then is we could solve for the speed of our object relative to the speed of light. And we could either just find it as a fraction of the speed of light, or again, this one's on the IB data sheet, we could put in the actual speed of light in meters per second. And we could use that to figure out how fast this galaxy is going relative to us as we observe it, since we see that shift of light. So the numerator is always going to be smaller than the denominator, so we'll end up with a speed that's less than the speed of light. If you ever get a speed bigger than the speed of light, you did something wrong, because nothing can go faster than c, the speed of light in a vacuum. This comes out to be 3 times 10 to the 7th meters per second, or we'd say 0.1 c. Okay? In other words, this ratio ends up being 0.1. Okay? So this galaxy is moving at 1/10 of the speed of light relative to us. And we can measure that based on the shift of the wavelengths. But I should also be able to tell whether this galaxy is moving towards me or away from me. So what do you think? The light should be 656, but it's showing up as 722 instead. Has this light been red shifted or blue shifted? It's a longer wave, right? Okay, so that's one thing you might be asked to do. It's red shifted. So not only do I know how fast it's moving, but it's also moving away rather than moving towards me in order to give off that longer wavelength. Okay, any questions? Okay, if you're in SL, you could go ahead and bow out now, and you could go ahead and start the activity. The last two example problems are particular to HL. We'll look at our frequency and source and observer equations. First one, I don't know if you ever played with one of these growing up. I always had these, we bought these footballs, these Nerf footballs that had whistles in them, and you'd throw them through the air and it'd make this high-pitched whistling sound. It would do the whole eew thing as it soared over your head. Okay. So the football has a whistle in it. The whistle makes a sound of 1020 hertz. The thrower hears 977 hertz. how fast does he throw the ball if that's the case? So we made a little sketch of this, what's going on. Okay, there's a whistling football, okay, and the football is the source of sound, so it's sending sound waves out. Okay, so we're trying to figure out what the speed of the source is as it sends waves out. And what we know is we know that the frequency of the source is 1020 hertz. That's the pitch of the whistle from the football. But it's not what the person hears, because the football is moving away from them. They hear a Doppler shifted sound, so the F prime is 977 hertz. They get a slightly lower pitch sound since the football is moving away from them. So based on how much lower the sound is, they should be able to predict their throwing speed. So this is about a moving source rather than a moving observer. So we'll use our moving source equation. F prime V over V plus or minus US, or US. And we'll put the 977 hertz in. Source is 1020. Speed of sound, about 343 meters per second. Put that in for our speed of sound. We're trying to solve for US. And I've got to make a choice about whether this is a plus or minus in the denominator. So what do you think it's going to be, Annie, a plus or a minus? So we're getting 977 out of this. We're multiplying 1020 by this fraction in parentheses, and we're getting something that's smaller than 1020. So it needs to be addition. This fraction has a bigger denominator than numerator, right? So that we end up with something less. So it's got to be plus. Okay. So then what we could multiply this, do the algebra to solve for US. I'll leave that up to you. Solve the algebra. It ends up being 15 meters per second, which is a reasonable speed for throwing a football. It's about 30 miles an hour. Okay. How fast the football is moving away from the person. The second question asks me, what frequency does a catcher hear? Okay, so now I know the source is going 15 meters per second. And there's a person over here ready to catch the football. And I know that the source is putting out 1020 hertz. Now we want to figure out what the observer hears. This time the football is moving toward the observer instead of away from it. So we're talking about the catcher instead of the thrower. It was the same formula. I'll write it out again. The source that's given off sound. We're solving now for F prime. 1020 hertz. 343 meters per second for the speed of sound. And we now know the source is going 15 meters per second. And I've got to make a choice as to whether to put the plus or the minus in the denominator. What do you think? Now it's the minus. Okay. Now the denominator should be less than the numerator so that we end up with a higher frequency. Otherwise, we're just going to get the 977 again, right? Okay. This person should hear a Doppler shift that's pitched higher. So, oh yeah. So this ends up being 1067 hertz as the football moves towards them. So it's fairly easy to use this equation. The slightly tricky part is just being careful about whether it's a plus or a minus. And what you can do is if you get an answer that doesn't make sense, they're hearing a sound that's lower pitch when you know they should be hearing higher, then maybe you picked the wrong sign. Final question, one slightly trickier. This would be a little bit more of a complex problem. We have an echolocation question. We have a bat, and the bat's sitting still, and it's emitting 212 kilohertz to detect an insect. And this is really how bats do detect insects. They send little clicks out, and then those clicks come back. The bat receives a reflected wave that's coming back at a higher frequency, which implies the insect's moving towards the bat, right? So we got a higher frequency Doppler shift. We need to find the actual speed of the insect as it flies back toward the bat. Okay. So what's a little bit strange about this problem is there's actually two Doppler shifts happening. There's a Doppler shift. Well, let's draw the picture. We'll kind of think this out. I didn't really practice drawing bats very much, so there's my blobby bat. Okay. The bat is producing the sound, and we're told that the frequency of the source of sound, so the bat, of course, is the source of the sound, and that source is 212 hertz. Okay. And so sound waves are coming out from the bat, and we got some kind of an insect. And we got the frequency ends up being higher, which suggests that the insect's moving toward the bat. We're trying to figure out what that speed is as the insect moves towards the bat. That's what we're looking for. What's the speed of the observer? Right? The moth isn't the one creating the sound. The bat is, right? Okay. So what's tricky about this is we don't actually know what the moth hears, and the bat doesn't know what the moth hears either. The bat gets the sound hits the moth and then it comes back to the bat, which makes the bat both a source and an observer of waves. So there are two things that happen here. We need to think about this in two steps. Okay. So the first thing we could do is just say, hey, what does the bug receive? What does the bug hear? It's not going to hear 212, it's going to hear a Doppler shifted sound. Okay. So we can figure that out by applying the Doppler equation. F prime equals F, and the observer is moving, so we have a moving observer. So we'll use our moving observer question. It's not the source that's moving. And we can find the frequency that the bat hears. We'll put the numbers in. 212 hertz. Speed of sound is 340. Notice that I made the choice of the positive sign in the numerator because the moth's moving towards the bat. It should get a higher pitch sound. Okay. Why did I pick 340 instead of 343? I used 343 on the previous page. Let me just be consistent. I don't have to round. We'll go with 343 again. Okay. 343 meters per second for the speed of sound. Again, that would probably be like a test question that would be given to you, be reminded of the speed of sound. The problem is there are two unknowns here. I don't know the speed of the moth, and I don't know what frequency the moth hears. Okay, so I have an equation that has both of those unknowns in it. Okay, so I actually need a second equation to solve this problem, an equation that involves the same two. Okay, so this frequency that the moth hears, this becomes the new source. And there's going to be a flipping now, okay, where now those reflected waves that are bouncing off the moth is now the source of the waves. I gotta draw a bat again. Not getting any better at drawing bats apparently. Okay, and now the bat is the observer. And we do know what the bat hears as the waves come back to the bat. We haven't used that number yet. We do know that F prime for the bat is 220 hertz. And so we have now this moth speed is the source speed. Okay, so that means we now need to use our moving source equation instead of our moving observer equation. V over V, and now it's the source that's moving. And again, the source is moving toward the observer, so it's going to be a minus in this case, because it's a higher pitch being created. So the Doppler shift is happening twice. It's happening first as it hits the moth, and then secondly as the moth continues to move, it bounces off and it moves back toward the bat. So if we plug the numbers into our second equation, we know the bat here is the 220 hertz. Okay. What we don't know is we don't know the frequency that's coming off of the moth. Okay. But that frequency is the solution to the previous equation, isn't it? It's the f prime right here that the moth heard. That corresponds, these are the same frequencies. And this is just the speed of sound, 343, 43 minus US. Okay. So there are two connections between these formulas, okay, that the frequency the moth hears becomes its frequency as the source. And actually these two U's, they're the same thing. They're both how fast the moth is flying, right? We have the speed of the moth when it's the observer and the speed of the moth when it's the source. It's the same number of meters per second. So I have two equations with the same two unknowns. And so we can solve this system of equations by substitution. And again, this is to do the algebra. Basically what I'll do is I'll take all of this equation and I'll plug it in. Since this is my frequency, I'll plug all of that in for this frequency here. And we'll just write it out. I get 220, and instead of F, I'll have 212. I'm going to leave the units off just for the sake of simplicity here. Plus U over 343. So this is F. And that's going to be multiplied by 343 over 343 minus U. And notice I'm just calling it U instead of source and observer because it's the same speed. It's the speed of the moth. It's the same unknown. So after making my substitution, I just end up with this expression where U is my only unknown variable. And again, I've got to do a little bit of algebra here. And we could cancel some things out. Like for instance, there's a 343 in the numerator and a 343 in the denominator. Those cancel out. Okay. And then I could solve for U. Just give you the end result. Ends up being 6.3 meters per second. I'm not showing all the steps of the algebra, but I'm sure you could do that. So that is the end of the lecture for the Doppler effect.